Assalamualaikum dan selamat sejahtera kepada semua. Okay, so kita continue with our class for Fluid Mechanics BNJ 20203 with another chapter which is chapter 6 in which kita akan analisis flow in pipes. Okay, so actually based on the title itself, when we say about analysis of flow in pipes, actually we are focusing on those that is related to the internal flow. And as I have discussed with you guys, I think in chapter 1 there are basically different types of flow that we can consider, and one part of it is sama ada dia adalah an external flow or internal flow. So when we say about analysis of flow in pipes, automatically it will be regarded as a internal flow, kan? Sebab dia internal flow sebab apa? Sebab dia ada boundary dia is bounded, kan? Dalam pipes dia dikelilingi oleh pipes. Okay, the flow is inside, kan? Kalau macam external flow, if you guys still remember, external flow it involve with the free stream. Okay, it involve the aerodynamics of a free stream. Okay, if let's say maybe for after this PSM who would like to continue with me, obviously kita akan buat something related to aerodynamic analysis. Okay, aerodynamic analysis for external flow. Okay, external flow tu lebih kepada flow dekat luar lah, kawasan luar, kan? Flow over a vehicle, flow over buildings, kan? And so on. Kalau pipes ni dia internal flow sebab dia kat dalam, and then apa lagi ya? Internal flow ni banyak juga sebenarnya. So the mechanics of flow dekat external dengan internal, dia guna almost similar concept, but the parameter is a bit different. Okay, later on kita akan go through lah what is the differences. Okay, so as for this topic, we are focusing on those with the internal flow. Okay, alright. So basically these are the objective that you are supposed to get within this chapter. Firstly, so that you have a much deeper understanding of lamina and turbulent. So bila kita cakap lamina and turbulent ni, rasanya you guys saya dah terangkan sebelum ni, what is lamina flow and what is turbulent flow. So somehow within this chapter dia akan classify further lah regarding the lamina and turbulent flow and in pipes analysis. Okay, so dia dah fokus kepada pipes analysis. Okay, secondly, the second objective is to calculate the losses involved associated with pipe flow in piping networks. Okay, so kita akan study what is the major losses and what is the minor losses kalau kita consider a fluid flow dalam pipes. Okay, and thirdly is to understand the different velocity and flow rate measurement techniques and learn their advantages and disadvantages. So kita akan go through later on as we go with this chapter. Okay, first of all, of course, apa-apa pun bila kita kata fluid flow, we need to know about Reynolds number. Reynolds number ni untuk apa? Dia adalah satu parameter, dimensionless parameter yang digunakan untuk menilai atau menilai the characteristic of or the behavior of satu-satu flow tu. Okay, dia yang akan menentukan sama ada satu-satu flow tu adalah lamina ke, turbulent ke, ataupun in transition between lamina or turbulent and so on and so forth. Okay, so we go through the definition here. The Reynolds number is actually defined as the ratio of the inertial forces to the viscous forces. Yang ni you need to know. So later on, if saya akan tunjuk the equations lah. That is why we call it the ratio of inertial forces to the viscous forces. And consequently quantifies the relative importance of these two types of forces for a given flow condition. Terus untuk satu-satu flow conditions tu um, kita akan nilai the characteristic of flow based on the ratio of inertial forces to the viscous forces, and they are used to, macam saya cakap tadi kan, Reynolds number ni is used to characterize the different flow regime within a similar fluid, such as either it is going to be laminar or turbulent. Okay, and ini konsep penting so jap saya tukar sikit. Okay, so usually laminar will occurs at lower Reynolds number in which the viscous forces are dominant. Okay, so yang ni kan sebab dia kata apa tadi Reynolds equals to inertial forces over the viscous forces kan. Okay, so when it says that the laminar flow occurs at lower Reynolds number means that the viscous forces are dominant lah. So bila this value besar, Reynolds berkurang lah kan. So senang je, kita tahu ini, kita dah boleh create the definition. Okay, and on the other hand, for turbulent flow, Reynolds number adalah tinggi, and it is somehow is dominated by the inertial forces, which is the forces dekat bahagian atas ni. So bila this value tinggi, the Reynolds will also be higher lah. Okay, so ini adalah contoh boundary layer inside pipes, fluid flow in pipes. Okay, and as we can see here, apa yang ditunjuk kat sini, kita ada turbulent dan kita ada laminar. So bentuk dia agak berbeza disebabkan dia punya karakteristik. So kalau kita tengok for turbulent flow, dia bentuk dipengaruhi oleh velocity. However, for laminar flow, dia punya shape of the boundary layer tu agak sekata. Okay, sebab kalau kita lihat, ini adalah velocity velocity. Ini semua ni sepatutnya velocity So kalau bila kata turbulent kan, turbulent untuk satu-satu flow tu, untuk jadi turbulent, dia mesti ada velocity yang tinggi. Okay, laminar ni velocity rendah. So bila dia kata velocity tinggi, that is why dia punya shape of this boundary layer almost sekata dan ditarik oleh velocity yang tinggi tu. Tapi kalau laminar flow, dia sebab velocity dia rendah, so dia tak dipengaruhi oleh this boundary kat atas dengan bawah ni. Tak apa, later on we will go further with the explanation lah. And bila velocity tinggi, Reynolds number pun akan tinggi. And bila velocity rendah, Reynolds number is rendah. And these are the criteria in which they differentiate based on the Reynolds number lah. Okay, so based on Reynolds number, kita boleh characterize sama ada dia turbulent or laminar. Okay, so based on this reference, dia ada basically different reference. The value of Reynolds number for turbulent and laminar is a bit different, but it depends on cases lah. But in general, we could say that for Reynolds number for turbulent, the Reynolds should be more than 4,000, and for a laminar, the Reynolds should be less than 2,000. And between 2,000 and 4,000, there is one other flow regime in which we call a transition regime, transition flow, in which kita tak boleh nak regard specifically sama ada dia laminar or turbulent. Okay. Okay, next. This is more details on Reynolds. It is actually, this equation is actually introduced by this Osborne Reynolds. Okay. Alright. And macam saya cakap tadi, it involve the ratio of inertial forces and viscous forces. So the inertial forces is the velocity times, if let's say flow in pipes, this would be the diameter of the pipes and also the density of the fluid over this dynamic viscosity, or else it will also be simplified to the velocity of the fluid times diameter of the pipe over the kinematic viscosity. So it is interchangeable between this and this. Disebabkan this kinematic viscosity is actually equals to the dynamic uh, dynamic viscosity over the density. Okay, bila kita replace dia akan jadi yang ni lah. Okay, samalah. So maksud dia if let's say kita ambil yang ni, okay, VD over rho, VD rho over mu, kita ganti this mu dengan sorry, saya dah terbalik ni. Okay, sekejap. Okay, actually this mu apa saya buat ni? Sorry. Betul lah tadi. Okay. This kinematic viscosity is actually this dynamic viscosity over rho. Okay. So untuk kita replace this, kita akan dapat VD rho over this kinematic viscosity times the density. So kita cancel out the density, kita akan dapat velocity times diameter of the pipes over the kinematic viscosity. Alright, this one. Okay, it is interchangeable based on this equation. Okay, right. So as we said earlier kan, macam saya cakap, this is bila kita cakap Reynolds number or flow related to internal flow. If let's say it is an external flow, this equation would be a bit different. Maybe this velocity is velocity of the fluid juga, tak ada masalah. And then kita ada, instead of diameter, sebab kita bila kita kata external flow, kita ada the characteristic length. Kita panggil characteristic length times density over this dynamic viscosity. Yang ni adalah berbeza. This is the characteristic length for external flow lah. Yang ni just knowledge tambahan untuk you guys. Okay, this characteristic length ni depends on apa yang kita nak simulate. Contohnya macam let's say kita nak create a vehicle, flow over a vehicle, this characteristic length can either be the height of the vehicle or the length of the vehicle or the width of the vehicle. That is why it is says as a characteristic length, in which kita boleh define sama ada height, length ataupun width. Okay. And then, okay, so kalau kat sini, maybe they refer to different kind of reference. So, it's stated here that if the Reynolds is less than 2,300, it will be a laminar flow. And more than 4,000 is turbulent flow. In between, it should be a transition flow. Okay, so apa lagi kita cakap kat sini? Reynolds number is directly proportional to the velocity and inversely proportional to the viscosity. Okay, so yang ni kita refer kepada dia punya rumus lah kan. So Reynolds number is directly proportional to the velocity sebab dia dekat atas, and inversely proportional to its viscosity sebab dia dekat bawah. Okay, so yang ni pun samalah. Okay, in between 2000 to 4000, it can be considered as a transition region, or also known as a critical region, in which flow can either be laminar or turbulent. It is a bit difficult to pin down exactly whether the flow is fully laminar or fully turbulent. Okay, now we continue with the chapter 6. Okay, in this slide, we introduce another parameter which is called the entry length. Entry length of the external, internal flow conditions. So what is entry length? By definition, entry length is the distance from the pipe entrance to the wall shear stress and thus the friction factor reaches within about 2% of the fully developed value, and it is actually the entrance length is actually the distance of flow that is travels after entering a pipe before the flow becomes fully developed. Okay, so this definition is much easier for you to understand lah. So what is the entrance length? Entrance length is the distance of a flow that is travels after entering a pipe before the flow become fully developed. Contohnya macam gambar dekat sebelah ni, figure kat sini. So sini kita ada flow that is travels after, masuk ke dalam satu pipe, is entering a pipe. Okay, as dia masuk with equal velocity. So as the flow move further inside the pipes, kita ada effects of this inviscid core due to wall shear stress, okay, or friction. Kat wall ni dia ada friction tau. Okay, bila ada friction ni, kita fikir logik lah. Bila kita ada friction, dia akan menyebabkan velocity akan jadi zero. That is why waktu awal masuk, velocity ada, tapi as dia masuk ke dalam, kat tepi ni terus jadi zero, kan? So anak panah tak ada tu, maksud dia zero velocity lah dekat wall ni. Okay, and maximum velocity waktu dekat tengah-tengah, V max. Okay, so what is entry length? By definition tadi dia kata apa? The flow become fully developed. Kalau kita tengok dekat sini, dia become fully developed dekat sini, in which dia punya boundary layer punya shape tu dah constant. It is fully developed, the boundary layer. So the entry length is the length in between dia punya entrance sampai dia jadi fully developed. This is what is called as the entrance length of the developing flow. Okay, senang kan? So maksudnya just jarak antara the position where the flow is entering the pipes until the flow become fully developed. This is called as the entrance length, and this table give you guys an approximation of the entry length for different types of flow conditions. So for laminar, usually it is can be regarded as a 0.05 of its Reynolds number, and this is for transition, and also this is for turbulence. Okay, this is, but you guys need to know this is just an approximation. Okay, and then another parameter that you should also know is the critical velocity. So critical velocity is the velocity of a liquid flow up to which its flow is streamlined, and after which its flow becomes turbulent. Okay, dia macam determinations between the fluid flow becomes turbulent. Dia akan apa-apa flow pun dia akan mula dengan laminar, and then by certain condition due to the structure of an object after the flow passes akan menyebabkan flow tu bertukar jadi turbulent. So this is what it calls as a critical velocity, in which a point when the velocity dah jadi turbulent. Yang tu cara mudah untuk cakap lah. Okay, so kalau kita tengok contoh gambar kat sebelah ni kan. So the first gambar sini. So this is actually a transition point in which laminar flow become turbulent. So kalau kita tengok sini, dia punya flow cantik je, smooth je. Tapi mai kat sini, dia dah ada separation. Bila ada separation ni, dia dah bertukar jadi turbulent. Okay, gambar kedua ni pun sama, kan? Tapi what is the differences between this flow and this flow is due to dia punya shape. Perbezaan shape sikit je pun akan affect dia punya flow structure. That is why it is important for us to study fluid mechanics. Sebab only sedikit perubahan ke atas satu-satu objek tu dia akan ubah everything and the fluid structure berubah, and then the aerodynamic loads berubah. That is why importance for us to study. Okay, especially kalau those saya bagi contoh lah, sebab saya pun dalam background automotive. So bila an object or vehicle lah, kita kata vehicle, kita buat satu flow analysis over a vehicle, kita ubah sikit je. Contohnya macam if let's say kita fokus on side mirror. Side mirror changes saja, dia akan ubah overall flow structure ke atas kereta tu, and then dia akan effect drag and as well as the performance of the vehicle. So bila drag bertambah, performance akan go down, and then it will affect the fuel consumption as well. So macam dia punya daripada design changes, everything will be affected as well. So kalau dekat sini kan, kalau kita tengok apa beza objek pertama ni dengan objek kedua ni. Okay, as we can see, the first object is more streamlined and the shape is more aerodynamics. So the position in which the flow changes from a laminar flow to turbulent is kat belakang sikit, a bit further downstream. Downstream kat belakang lah, sini upstream, sini downstream. Bila kita downstream. Okay, bila kita cakap pasal fluid flow, apa-apa yang kat bahagian depan kita panggil upstream, kat belakang downstream. So kalau the object is more aerodynamics, the position of the critical velocity or transition point from a laminar to turbulent flow is a bit downstream. Okay, it's further downstream as compared to this one. And so kalau kita tengok sini, dia shape dia lebih aero compared to this one. Okay, and the critical velocity depends on the coefficient of viscosity. This is the mu here, the density, and also the radius of the tube. Okay, so K is actually the constant proportional. Yang ni if let's say kita nak dapatkan the value of critical velocity lah. Okay, this is generalization yang kita boleh buat lah. Okay, macam saya cakap tadi, awal-awal semua laminar, tapi mai kat sini due to changes in object, dia akan ada suppression. Suppression ni akan menyebabkan flow tu berubah. Okay, so lama-lama dia akan jadi lagi besar lah. Okay, this is what we call vortex. Vortex in which lagi besar dia, lagi tinggi coefficient of drag kita. Okay, yang ni yang kita nak reduce. Kalau in vehicle lah, in vehicle performance, we would like to reduce this part in order to increase the performance of a vehicle. Itu sebagai contoh lah. Okay, so this is what we tell about this critical velocity. Okay, now we proceed. Yang tadi semua lebih kepada definitions. So now kita akan baru betul-betul kepada flow in pipes. Okay, flow in pipes, to describe any of these flows, kita akan guna conservation of mass, conservation of momentum, semua yang kita dah belajar sebelum ni, kan? Dengan energy equation, which is the Bernoulli equation as well. Okay, so if let's say kita nak buat analysis of flow in pipes, these are the important key point that we should take note. Okay, kita kena tahu the fluid flow must be a Newtonian, in which the fluid must be constant in density, and it must be isothermal as well, in which the temperature would be constant, and then it must also be incompressible, means that it does not depend on pressure, it is independent of pressure differences. And then the flow is considered a steady flow independent of time, and it is also a laminar flow in which the velocity has only one single component. Okay, and for last one ni actually kita akan consider both if let's say the flow is laminar or turbulent as well. Okay, later on kita akan go through few example, don't worry. Okay, so types of flow in pipes and how they influence energy losses in pipes. So macam saya cakap tadi, flow can be differentiate into two, in which laminar and turbulent. So sekarang ni kita consider laminar dulu. Okay, so for a laminar flow, it is a flow where the fluid move slowly in layers in a pipe without much mixing among the layers. Kan, kalau kita tengok dekat sini, ni contoh lah. Dia ada injection tube sini, dia keluarkan dye stream, dia flow tu smooth je, tak ada apa-apa perubahan pun. Okay, so when we go in detail dekat sini, actually no, bukan kat sini, ini sebenarnya contoh lain. Okay, so if let's say flow masuk ke dalam satu-satu pipe tu, kita dapat tengok dia punya flow tu smooth je. Okay, yang ni gambar macam tadi lah. Dia ada entry length, dia ada flow, fully developed flow region. Okay, cumanya for laminar flow, the entry length dia lagi rendah lah compared to entry length for a turbulent flow. Okay, for this laminar flow, it typically occurs when the velocity is low or the fluid is very viscous. Okay, so kita tengok balik rumusan apa pun, in any explanation in fluid mechanics, it is the best if you could refer back to the equations. So what is Reynolds? Reynolds is density times the velocity and times the diameter of the parts over the dynamic viscosity. So as we can see here, it says here, for a laminar flow typically occurs when the velocity is low. Kan, logik tak? This velocity must be low in order for the Reynolds number to be low. Kan, so bila kita kata laminar flow, Reynolds number low kan, less than 2000. In order to make it low, the velocity of the fluid must be low. That's why dia kata dekat sini, velocity is low. Okay, alright. And this is let's say kita nak dapatkan velocity profile lah. Okay, alright. So next is turbulent flow. And turbulent flow ni it is opposite of laminar, of course, where dia ada considerable mixing occurs, velocity and the velocities can be considered high. Okay, so kalau tengok contoh dekat sini and yang ni contoh tadi kan, the streamline of the flow dye stream is stable, dia cantik je. Tapi for turbulent, kita dapat lihat macam mana bentuk dia, and very disorganized. And this is what you call as a turbulent flow, in which velocity dia tinggi. Okay, so contoh lain adalah yang ni, yang kita dapat tengok dekat sini juga. If let's say a flow dalam satu pipes yang berbeza diameter, as the flow enter much lower area, and the flow will be turbulent. Okay, so yang ni sebenarnya kita boleh relate to the previously equation yang kita tahu, which is the flow rate equals to A times V, in which the velocity is Q over A, means that if let's say A is lower, V is much higher. Okay, alright, the velocity is higher waktu dalam keadaan very small diameter pipes, ataupun kita guna konsep Bernoulli lah, senang. Bernoulli konsep dia cakap apa? Bila pressure tinggi, velocity rendah, and bila pressure rendah, velocity tinggi. So dekat this area, the velocity is tinggi, the pressure is tinggi, so the velocity is rendah. However, dekat sini the pressure is rendah but the velocity is tinggi. Okay, Right, that is the differences between this laminar flow and also this turbulent flow. Okay, and laminar and turbulent flow can be characterized using the quantified Reynolds number lah. Okay, macam yang saya cakap sebelum ni, apa-apa pun untuk classify the differences between turbulent and laminar, it can kita boleh refer to the Reynolds number. Ini contoh lah, contoh air kan. Air yang keluar dari pipes tu asal-asal dia elok je. This is called the laminar. But however, as it splash down dekat sink, it will become turbulent. Okay, right. Next, okay, this is lebih more explanation on the turbulent flow. Let me see what apa yang diceritakan kat sini. When the fluid flow at high flow rates, okay, the streamlines are not steady, of course, and straight, and not steady and straight, and the flow is not laminar. And dia kata, bila kita kata turbulent ni, dia opposite of laminar lah, in which the flow rates will be higher lah. Okay, so generally the flow field will vary in both space and time, kan? So kalau kita tengok dekat sini the velocity of the average velocity in different position is fluctuate, fluctuate atas bawah ni, kan? Dia tak stable, kan? And these fluctuations comprise of a turbulence. Okay, for this case, kan, kalau kita tengok dari sini, ini in terms of z direction, ini in terms of a radial direction, both are fluctuating. Same occurs bila pressure. This x-axis is considered as time. Okay, so maksud dia time berubah, the fluctuation of the velocity and pressure is berubah. Okay, so how do we solve this kind of situations if let's say kita nak consider or nak selesaikan satu fluid flow problems, and one of the solutions yang kita boleh guna adalah kita kena guna Navier-Stokes equations. So bila kita kata Navier-Stokes equation, these are all the parameters that we need to consider. Actually Navier-Stokes equations ni yang ni dah lebih kepada fluid flow problems and solving lah, analysis, in which bila you guys using the CFD, computational fluid dynamics, kita akan ada banyak solver yang kita boleh guna, sama ada runs atau uruns atau LES atau DNS, dan ada beberapa lagi lah. And the most easiest one is, if let's say we consider runs lah. Runs and uruns is actually the same, just that runs is for steady flow conditions and urun is for the unsteady flow condition U, in which dia akan guna this runs method, in which runs itself is a Reynolds average Navier-Stokes equation. And dia apply this Navier-Stokes equation, in which dia akan average kan this value, the velocity value and pressure value, so that we can proceed with further discussion on this part. Okay, so ini tak ada, ini actually tak akan masuk dalam korang punya final pun, cumanya additional knowledge yang saya boleh berilah. Ini bila kita cakap pasal turbulent flow lah, macam mana kita nak solve this kind of situations in the real life, kita kena apply other equation as well. Alright, so yang ni adalah contoh Reynolds number kalau dalam badan kita, kalau dekat blood flow dalam brain kita agak laminar, in kita punya aorta. Aorta ni adalah salah satu saluran dekat kita punya jantung, paru-paru. Mana tak silap saya dia keluarkan oksigen kot. Alright. And then dia keluarkan oksigen ataupun dia keluarkan carbon, dia masukkan oksigen atau dia keluarkan carbon dioxide, something lah. Okay, and then if let's say for a typical pitch in a major league baseball, more than 200,000 Reynolds number, okay, in which dah masuk turbulent flow, and then 300 million Reynolds for a blue whale swimming in the sea. Okay, yang ni dah considered turbulent. Okay, ini dah yang ni laminar. Okay, so actually apa-apa jenis fluid flow pun kita boleh consider, kita boleh characterize based on Reynolds number, kan? So that is why this Reynolds number is very important untuk kita tahu. And then kita kena tahu equation dia, apa bahagi apa, in order to calculate this Reynolds number, and then based on the characteristic of the laminar or turbulent, kita boleh selesaikan satu-satu masalah fluid flow problems tu. Okay, so ini adalah satu contoh for Reynolds number. Senang je lah contoh ni. So determine the Reynolds number untuk this glycerin at 25 degrees Celsius, and given that this glycerin is moving in a pipe that has a diameter of 0.15 meter, and the fluid itself is moving at a 3.6 meter per second velocity. It has a density of 1258 kilogram per meter cube, and then it has a dynamic viscosity of 0.96 kilogram per meter second. So kita guna these equations, and then kita replace for the velocity, the diameter of the pipes, and then the density of the glycerin, and divided by the dynamic viscosity, and then kita akan dapat 708. And then kita boleh classify, since the Reynolds number is less than 2000, kita boleh consider the flow as a laminar flow. Very easy, kan? Okay guys, now we go much deeper into the chapter, in which this part kita akan sentuh mengenai friction losses in pipes. Okay, so bila kita kata pipes tu, dia ada banyak losses yang kita kena consider, and one of it is friction losses. And these losses is actually vary if let's say the flow is laminar or turbulent. Okay, it depends on the flow characteristics lah. Okay, so whatever it is, macam saya cakap sebelum ni kan, in solving fluid mechanics problems, kita kena involve those related equations, and for this one kita akan refer back to our energy equation, or the Bernoulli lah, and macam yang kita cakap sebelum ni, yang mana kita ada pressure term, kita ada elevation term, and kita ada velocity terms. And actually untuk kira friction losses, kita kena add on few either items on the left or on the right, depends on the situations lah. Okay, this is at one point, at the second point on the right hand side, in which this additional item ni kita boleh consider sebagai HA, HR or HL, in which HA is the additions. Usually kita add on energy lah, and this is an energy equation. So bila kita plus, maksudnya kita add on additional energy, and usually untuk case pipes ni kita add on pumps lah, bila kita pumps, dia akan add on energy to the fluid flow in pipes. Okay, so lepas tu kita akan tolak the removal HR, and also some sort of a friction loss, which is HL. Okay, so it depends on situation. Dia ada losses and dia ada add-on energy. Okay, so this is how we calculate the pressure losses. Okay, ini tak apa, tak penting sangat lah. Okay, so okay, actually friction losses ni pun macam kita cakap tadi kan, dia depends on the flow characteristic, sama dia laminar or turbulent. Okay, so yang pentingnya sekarang adalah kita kena tahu, if let's say a laminar or if let's say a turbulent, apa friction factor yang kita kena consider. Friction factor ni penting sebab friction factor ni yang akan affect kita punya value, the value of losses due to friction. Okay, so if it is a laminar flow, by equation kita boleh refer to the friction factor is equal to 64 over the Reynolds number. And if let's say for turbulent, kita boleh guna Colebrook equation lah. Okay, in which this is the friction factor yang kita nak dapat. Sebab apa kita perlu cari friction factor ni? Sebab kita akan guna balik dalam rumus head loss. Head loss due to friction. Okay, the friction losses lah. Okay, in which head loss equals to delta pressure in which this one the pressure loss, okay, over rho g ataupun equals to F L V average square over D2G. Selalunya equation ni lah yang paling penting. Equations in which apply for both conditions, either it is a laminar or turbulent, in which kita guna friction factor untuk dapatkan this value dulu. Yang lain-lain tu depends on situation lah. The length of the pipes, the velocity of the fluid, the diameter of the pipe and the gravity. Okay, this is how we calculate the head loss due to friction. Okay, penting kan ni? The friction factor for laminar, the friction factor for turbulent, and also the equation to calculate the head loss. Actually kan, untuk cari friction factor ni, dia ada dua kaedah. Sama ada this one, kita guna these equations in order to find the friction factor, or the other method is by using a diagram. So later saya akan tunjuklah macam mana kita nak refer to diagram, and in which option that you need to apply later on. If let's say the question asks you to find a friction factor, it depends on the question itself. Sama ada dia suruh refer to model diagram, or you can either use the equation. Okay, and this is the example on how we determine the head loss. Okay, so given that a glycerin at 25 degrees Celsius with the length of 30 meter of the pipes, the diameter of the pipe is 0.15 meter, and then the velocity, the density, and also the dynamic viscosity. Dynamic viscosity ni nak senang kita buat kilogram per meter second lah, SI units. Okay, so apa-apa pun kena ingat to solve this question, first of all we need to classify what types of flow. By this given information, kita kena dapatkan Reynolds number dulu, sebab Reynolds number ni akan classify sama ada flow tu turbulent ataupun laminar. So we replace all the information given in the equation. Okay, so kita akan dapat the value is 786. Since the value is less than 2000, we can consider it is a laminar flow. Kalau laminar flow, kita nak proceed macam mana? Next kita kena find apa? The friction factor kan. This is the friction factor. If it is laminar, kita guna 64 over RE. Kita guna this equation to find the friction factor. So when we replace the value of RE, kita akan dapat dan juga kita replace the equation for head loss. Kita akan masukkan yang ni dekat sini. Kita akan dapat the value of head loss equals to 13.2 meter. Senang je sebenarnya kan. So kita dapat daripada information given, kita dapatkan Reynolds number. Daripada Reynolds number, kita boleh dapatkan friction factor. Daripada friction factor, kita boleh dapatkan the head loss due to the friction. Okay. So ini sedikit penerangan lah mengenai friction losses for a turbulent flow. So macam tadi kita ada laminar dengan turbulent. And for laminar, we got a nice equation to compute the friction factor, in which kalau kita tengok equation dia sini, dia hanya depends on Reynolds number, which is this one. However, in case of turbulent flow, friction factor computed based on the inside roughness, which is this one. And tadi korang tak perasan kan, sekarang baru kita nak introduce dengan Reynolds number. And kalau kita tengok dari equation ni, dua benda penting. Kalau kat sini Reynolds number je, tapi kalau for turbulent kita ada Reynolds and the inside roughness, in which this epsilon, kalau yang ni contohnya ini satu pipes, ada inside diameter, lepas tu dekat surface of the pipes tu kita ada this surface roughness. Kita panggil yang ni surface roughness lah, this epsilon, surface roughness. Okay, and usually kita express it in dimensionless form, in which we create something like this relative roughness dependency. Okay, kita divide the diameter of the pipe, in which adalah this one, tengok tinggi dia, over the surface roughness, and supaya kita akan dapat dimensionless form Faham kan dimensionless form? Sebab diameter is contohnya in meter, bahagi this epsilon is also in meter. So kita boleh cancel out, kita akan dapat value of dimensionless. Sama macam Reynolds number. Reynolds number pun adalah satu dimensionless parameter. Okay, so if let's say kita refer to this diagram, if let's say it is a more rough pipe, kita akan dapat low d over epsilon. Betul tak? Sebab this epsilon value sangat besar. Bila kita kata rough, so maksud dia benda ni lagi besar lah, kan? So bila besar, denominator akan jadi besar, so it will reduce this relative roughness, and then that's why dia akan jadi low relative roughness for more rough pipe. And on the other hand, for much lesser rough pipe, kita akan dapat high relative roughness. This is the opposite condition of the more rough pipes lah. Ini kita boleh fikir logik lah based on these equations. Okay, so what else here? Friction factor for turbulent flow, relative roughness and Reynolds number, roughness value for various pipe can be referred to next table. Usually this pipe roughness will be given lah for different material. Kita akan dapat different value of pipe roughness. Okay, as pipe roughness makin meningkat, maksud dia lagi rough lah, dia lagi kasar surface dia. Okay, alright, next kita refer balik apa ada lagi. Okay, and this also some other value for roughness. So if let's say in the question, usually this is given, or sama ada dalam soalan ataupun maybe appendix dekat reference, dia akan bagi this table in which you need to refer. So kena tahulah, if let's say dia kata plastik, kita guna plastik punya roughness, steel punya roughness and so on. Jangan interchange pula, sebab surface friction ni dia bergantung pada material apa yang diguna pakai. Okay, so surface roughness, bila kita kata macam saya cakap tadi yang ni lebih kepada dia punya summary. Bila kita nak kaji pasal surface roughness ataupun losses due to friction in which depends on surface roughness, kita kena add additional dimensionless group which is the diameter dibahagi dengan surface roughness epsilon, in which need to be characterized, and thus more than one curve on friction factor Reynolds number plot. Okay, ini yang saya cakap tadi. In order to find the friction factor, kita boleh guna additional solution. Sama ada tadi tu saya cakap kita guna equations, and this part maybe kita boleh guna diagram as well. So diagram yang kita boleh refer adalah sama ada fanning diagram or a Moody diagram. But for your for your reference, for this chapter kita akan more focus on the Moody diagram lah. Kita pilih salah satu sahaja. Okay, no problem, because usually Moody diagram is much popular compared to the fanning diagram. Okay, for a laminar region, usually lah, for fanning chart kita guna friction factor equals to 16 over Reynolds, and for Moody chart kita guna F equals to 64 over Reynolds. Yang ni sama je macam tadi kan, for a laminar. So kalau kita tengok sini ni contoh. So sorry, saya counting banyak pula dekat sini. Tak apa, saya buang balik color-color ni, saya explain balik lah. Okay, kalau kita tengok dekat sini this is an example of a Moody diagram in which it is actually developed untuk kita dapatkan value of friction factor. This value of F for various relative roughness and Reynolds number. Kan? So apa? Macam saya cakap tadi, usually soalan, apa-apa yang paling penting pun kita dapatkan Reynolds number dulu. Bila kita dah dapat Reynolds number, kita kena dapatkan friction factor. Friction factor ni pula bergantung kepada condition, yang sama ada dia laminar atau turbulent. Kalau laminar senang, kita guna equation dia pun simple. Kalau turbulent ni sebab dia bergantung kepada surface roughness dan juga surface roughness dan juga Reynolds, it is a bit difficult to find the value of surface friction factor ni, in which dia bergantung pada characteristic of the parts jugalah, sama ada turbulent ataupun laminar. Okay, so kalau kita tengok dekat graf ni, untuk Moody diagram, x-axis kita ada Reynolds number. Saya guna ni lah. Okay, and then the y-axis on the right hand side kita ada d over epsilon. Kan? What is d over epsilon? D over epsilon yang tadi saya introduce kan. Sekejap saya tunjuk balik. D over epsilon is the relative roughness. Okay, relative roughness. Okay, this tak apa, saya tulis balik kat sini. Relative roughness dia. So usually from the question, kita akan dapatkan Reynolds number, kita akan dapatkan relative roughness. Lepas tu baru kita akan dapat dia punya value of friction factor dia, in which on the left hand side here. Okay, so kalau kita tengok graf ni lah, nak mudahkan. Kita tengok graf ni, kita ada laminar zone here, kan? This is laminar. Saya lukis sikit, laminar zone. So apa-apa less than 2000, kan, Reynolds number than 2000, kita boleh panggil laminar zone. Okay, so in between 2000 and 4000 is the critical zone, disebabkan value dia antara laminar dan juga turbulent. And then on the right hand side kita boleh panggil dia turbulent. Okay, semua yang ke kanan lah. Okay, alright. So for a given material, contohnya lah, kita ambil satu contoh kan. Kalau kat laminar zone senang, value dia sama. Tapi kalau dekat as the Reynolds increases, it depends on the macam tadi cakap kan. Kalau tengok dekat sini, for a laminar flow, the friction factor only depends on Reynolds number. Betul tak? Kalau kita tengok kat sini, Kan? The value depends on Reynolds number je. Bawah je. Dia tak ada banyak line macam dekat higher Reynolds number. Kan? For lamina kita ada satu line je, in which depends on Reynolds number sahaja. Tapi kalau turbulent flow, dia kata apa tadi? Dia depend on inside roughness, in which the relative roughness lah, D over E dengan Reynolds number. Kan? Kalau kita tengok belah kanan ni, dia bukan hanya bergantung pada ni, dia bergantung pada relative roughness juga. That's why dia ada contoh untuk satu material ni, line dia macam ni. Satu material ni, line dia macam ni. Satu material ni, line dia macam ni. Dan satu material ni, line dia macam ni. Berbeza-beza depend on the relative roughness of the relative roughness of these pipes. Okay. And actually this is ada satu lagi line kat sini. Saya akan tunjuk. Dividing line between complete turbulence and transition zone. Okay. Kalau kita tengok dekat sini kan, dekat bahagian sini, semua dah tak ada effect of Reynolds number. Siapa-siapa yang atas daripada transition zone ataupun a complete turbulent, kita boleh kata no effect on RE dah. Reynolds number dah tak ada, almost tak ada affected dah. Dia dah dah consistent dah the value. And cuma yang berbeza dia hanya dekat bahagian this transition zone. That's why transition zone ni sebenarnya payah sikit. Dia macam everything is not consistent. Kan? Dia the value is varies depends on relative roughness. So berbeza-beza. If let's say dia dah capai fully turbulent, kan? Dah lalu sini, the value, color apa lagi saya nak guna okay, the value dah consistent. This is what it means by no Reynolds number effect for a complete turbulence region, in which belah kanan ni. Okay. So banyak sikit nak kena hadam daripada this diagram. Tapi if let's say korang betul-betul faham, it is actually mudah aja sebenarnya. Okay. Alright. So bila kita kata Moody diagram ni, bentuk dia pun berbeza-beza. Kalau kita tengok ini kat sini sekarang, the relative roughness is D over epsilon. Kan? Kalau dekat sini it a bit different. Dia yang ni sama, D over epsilon juga. Okay. Dia ada certain condition in which dia boleh kata the relative roughness is epsilon over D. Tak ada masalah. Depends on situation. Kan? Tapi the graph is sama juga. Kan? Kalau kita tengok kan, sini dekat bahagian lamina, and then this is bahagian complete turbulence. Kan? Lamina dia satu je line. Complete turbulence dia banyak line, depends on to relative roughness, tapi value dia constant. Kan? Belah kanan ni. It depends on material lah. Okay. However, dekat transition sahaja yang dia ada berbeza-beza. Depends on Reynolds number. Reynolds number kat bahagian bawah ni. Kan? Alright. So, ini pun contoh another Moody diagram lah. So, basically Moody diagram ni bentuk dia sama je. Cuma yang berbeza-beza dia hanyalah pada part C sini je. Okay. Maybe berbeza sikit lah. Depends on questions. Okay. So, this is a bit summary or key points about important key points about Moody diagram. So, in the lamina zone, F decreases as RE increases. Betul tak? And kalau kita tengok sini, in lamina zone, which is sebelah kiri ni, the value of friction factor here decreases as the Reynolds number increases. Betul tak? Dia berkurang value of ni friction factor berkurang as the Reynolds number meningkat. Okay, this point is clear. And then the friction factor is equals to 64 over RE. Okay, so ini line ni adalah F dia equals to 64 over RE. That's why kita dapat straight line je. Okay, and then kita ada transition zone which is almost not possible to predict. Okay, so which is this one. Okay, this area. Okay, and then kita ada for a given relative roughness. Okay, for a given relative roughness kat sini. Okay, friction factor decreases with increasing Reynolds number till the zone of complete turbulence. Okay, so kita dapat lihat for a given this relative roughness, the friction factor berkurang. Nampak semua turun. Semua ke bawah as Reynolds number increases until dia jumpa complete turbulence before dia jadi almost constant. Kan? Banyak kali saya ulang benda ni kan. Hopefully you guys can understand. Okay, and within the zone of complete turbulence, Reynolds number has no effect. Kan? Dah complete turbulence yang dah belah kanan ni, tak kisahlah Reynolds number dia berapa pun, kan? Dia increase, tak kisah, dia akan friction factor akan what we call it consistent, stagnant, and the value will be the same. Alright, so kita go for another example. Okay, sorry kat sini pun saya ada counting sikit. So disuruh determine a friction factor if water at 70 degrees Celsius is flowing at 140 meter per second given V in an uncoated ductile iron pipe having an inside diameter of 0.025 meter. So determines the Reynolds number. So dia nak suruh kira F. Macam biasa, before kita nak kira F, kita nak tahu dulu characteristic of the flow. Nak dapatkan characteristic of the flow, kita guna Reynolds number. So using all the information given here, kita boleh dapatkan value of Reynolds. Bila kita tengok value of Reynolds ni sangat tinggi, which is more than 4,000. Kan? Yang ni dah millions dah ni. So kita boleh consider it is a turbulent flow. Betul tak? Okay, so now kita dah tahu dia turbulent flow. And then macam mana kita nak dapat friction factor? Kita boleh guna Moody diagram. Okay, first of all, bila kita nak guna Moody diagram, kita kena ingat apa yang kita nak kena tahu. Kita tahu yang ni dia punya Moody diagram. Dah hafal lah kan? So sini dia punya relative roughness, sama ada D over E ataupun E over D, depends on which graph are we going to use. The x-axis is Reynolds and this is the friction factor yang kita nak dapat. So sekarang kita dah tahu ni. In order to get this, kita kena dapat satu lagi information which is ni. Diameter dah ada, diberi kan diameter dia. Sekejap, saya ambil color lain. Diameter dia, inside diameter dah diberi. So kita nak kena dapatkan dia punya surface roughness. So kita dah tahu given is ductile iron. So kita refer balik table tadi. Table ada bagi tahu tak pasal ductile iron. Ductile iron, iron lah. Iron 2.4 kali 10 kosong negatif 4. This is the surface roughness. Kita boleh guna. Okay, so bila kita guna, kita masuk balik dalam equation. Okay, kita guna ni 2.4 D over E dia. Lepas tu kita akan gunalah this value at 0.0025 dengan at Reynolds number ni. Kita use saya ambil kita guna Reynolds number ni RE dengan kita guna this value D over E ni. Yang ni sama dengan berapa Yang ni sama dengan, sekejap saya nak hitung. 0.025 divided by 2.4 times 10 to the power of minus 4. Okay, you guys should get around 104. Oh, dah ada dah kat sini. Shit. Okay, so 104 dekat sini. So kita guna this two number. This is the uh, apa? The relative roughness, which is 104. Sekejap, saya guna pen ni. 104. Relative roughness equals 104 dengan Reynolds number tadi. Kita dapat berapa? Tulis dekat Moody diagram siap-siap. 8.43 kali 10 kuasa 6. 8.43 kali 10 kuasa 6. Okay. Alright. So, ini saya terlepas tadi. Untuk kira this Reynolds, since the kinematic viscosity tak diberi kan, ataupun ini depends lah yang mana kita nak guna. Actually, kita kena boleh refer table lah kan. Macam dia kata kat sini kan, at temperature 70 degree Celsius dengan water kan, kita boleh guna water punya properties punya table at 70 degree. Sama ada kita nak ambil dynamic viscosity or kinematic viscosity, kita boleh guna the value lah. Okay, so untuk this case kita guna this saya rasa this kinematic viscosity 4.15 times 10 to the power of minus 7. Okay, so kita dah dapat dua value ni. Macam mana kita nak buat? First of all, kita kena tengok kat mana relative roughness dia. Around 100 lah kat situ. That's why kita bulat kat sini 100. Lepas tu kita kena tengok juga Reynolds number kita around berapa. So 8.43 kali 10 kuasa 6, sini 10 kuasa 6 dekat 8. So lebih kurang dekat sini lah. That is why saya ambil this value and then dia bersilang dengan sini. So the fraction factor punya value dia adalah somewhere dekat sini. Dekat titik persilangan. And then untuk point ni kita akan dapat this value of fraction factor, in which equal lebih kurang lah 0.038, a bit below 0.04. Senang kan? So daripada fraction daripada details on the fluid flow dalam pipes tu, kita dapatkan Reynolds number dia. Lepas tu kita based on Moody diagram, kita dapatkan dia punya friction factor. Okay, kita continue dengan head losses in pipes. So this is a bit of an introduction. Sebenarnya kita dah sentuh dah bahagian ni tadi, cuma dia lebih spesifik on this area, in which sebelum ni kita head losses saya dah define in general. Dia ada addition, removal dan satu lagi itulah HA, HL dan apa lagi satu ni, satu pun dah terlupa tadi. HA, and what is the other one is friction. Dan mengenai friction saya dah sentuh banyak dah tadi on how frictions affects the losses in pipes kan. Right, so okay, not this one, this one. Right, yang ni ke? Sorry, sekejap tadi. Oh yeah, this one. Okay, so this is a bit of a definition on head losses. Head losses in pipe refers to the pressure drop, especially due to friction. Yang ni yang macam kita dah sentuh tadi sebenarnya. As a fluid flow through a pipe, head losses represent how much pressure will be lost due to the orientation of the pipe system. And this is used to actually determine the optimum efficiency of the pipe system. Okay, so macam yang saya introduce tadi, head losses can be calculated using this formula if it involve friction. Okay, And head losses also depends on the input velocity of the fluid flow, the density of the fluid and also the orientation of the pipe system. Oh, yang ni kita akan tengok lah. Kan sebelum ni kita hanya introduce to the losses due to frictions. However, due to the orientation of the pipe system, macam kalau dia ada bend ke, dia bentuk-bentuk dia horizontal or vertical, dia ada effect juga kepada losses in pipe system. Head loss can also be influenced by surface roughness, okay, yang ni, on the inside of the pipe, yang seperti yang kita terangkan tadi, and in the addition to the pipe and fittings, valve and other devices that is installed in the piping can also contribute to head loss. Okay, dia adalah beberapa items yang kita will need to consider in order to sum ataupun untuk calculate the total losses in pipe system. Okay, ini adalah beberapa contoh lah. Okay. So, macam saya mention tadi, kita akan guna Bernoulli equation or energy equation in order to calculate the losses. Kan, yang ni pun yang saya dah tunjuk tadi. Okay, so energy could have been supplied by introducing a pump. Kan, bila kita introduce pump, kita actually supply the energy, which is the HA yang kita apply tadi. And equally could have been lost by doing work against friction or in a machine such as turbine. So, yang ni dengan yang ni adalah losses dia. So, kita combine semua ni untuk capai the head losses lah. Ataupun, kita juga boleh bawa this equation kepada kanan lah. Ke kanan, in which yang minus-minus tu, dia dah jadi positif-positif dekat sini, yang pump tadi positif on the left hand side, dia jadi minus on the right hand side. Okay, this one. Okay, dia tak kisahlah kita nak letak kat mana pun, yang penting kita faham what is the definition. Okay, and the energy equation can be expressed in terms of head and head loss by dividing each term by the specific of the fluid. So, bila kita divide all these term in energy equation by a specific weight, actually the total head in a fluid flow in a turbine or a duct can be expressed as the sum of elevation head. So, yang ni akan jadi the elevation head. So, saya buat macam tu je lah. And this is the velocity head. And this one is the pressure head. Okay. Okay. Kat sini dia akan classify sikit lah. Bila kita kata head losses in pipes tu, kita akan be specific. Okay. Dia ada, sama ada kita boleh consider as a major losses or minor losses. So, which one is major losses? Which one is minor losses? So, the contribution from major losses and minor losses ni yang akan sum the total losses in pipes. So, yang ni benda penting yang you guys need to take note. The total losses, total head loss in the pipe system is equivalent to the summation of major losses plus the minor losses. What is major losses? Major losses is due to friction in pipes and duct system. Okay. Kalau kita cakap pasal friction yang seperti yang kita kira tadi, yang tu semua adalah contributed by the major losses. On the other hand, for the minor losses, this is due to the components in the system. Components. And components such as valve ataupun orientation of the pipe itself, the bend ke, tease ke, and also change in bila orientation dia berbeza, dia akan ada change in velocity as well. Okay, so bezakan which one is major, which one is minor losses. Okay, this is a bit of summary sikit lah, and about fat flow punya head loss. So, bila kita kata losses, equation yang penting, seperti yang kita tahu, this one. Alright, so pipe flow head loss is actually proportional to the length of the pipe. Betul tak? So kita tengok equation ni. Yes, dia ada kat atas, dia proportional. So length lagi panjang, head loss lagi panjang, lagi tinggi. Kan? Itu logik lah. Lagi panjang satu-satu pipe tu, lagi tinggi lah losses yang dia dikenakan ke atas fluid flow tu. And then dia juga proportional to the square of the velocity. Betul kan? V squared. Kan? Lagi tinggi velocity, lagi tinggi losses dia. Means that lagi tinggi Reynolds number, lagi tinggi losses dia. And also means that lagi turbulent flow tu, lagi tinggi losses dia. Okay. Dia juga inversely proportional to the diameter of the pipe. Okay. So, if let's say diameter pipe lagi besar, lagi bagus lah. Kalau diameter lagi kecil, lagi tinggi losses dia. Okay. Dia terbalik. That's why dia kata proportionally inversely. Okay. And also dia increasing with surface roughness. So surface roughness tinggi, surface roughness kan daripada surface friction kat sini kan. Friction factor kat sini. So lagi tinggi surface roughness, lagi tinggi the value of head loss. And also the total losses adalah daripada minor plus major losses lah. Okay, which involve kalau major ni all the friction. Okay, kalau minor ni daripada all the elements yang kita add up, and also orientation of the pipe itself. Okay, ini pun lebih kepada sama juga macam tadi. Cuma definition dia kita just bagi from different perspective on how we regard the major losses and minor losses. Tak apa, kita go through banyak kali supaya insyaAllah lebih mudah untuk korang faham lah. So the losses in pipes kita boleh divide major and minor. Major is due to friction and minor due to the change of velocity due to bends or orientation of the pipe itself. And also if let's say kita ada a valve or pump, valve, ada valve kat situ lah, in which dia akan contribute to minor losses. Okay, what else? Kalau kita tengok dekat gambar ni, gambar ni is much easier lah for us to classify which one is major losses and which one is minor losses. So major losses kita dapat lihat yang pada kuning ni. Kuning ni semua sebab dia ada friction friction pada pipes. Okay. And then minor losses due to kat sini dia ada entrance, dia ada exit. Bentuk exit, bentuk entrance ni adalah dia punya orientation lah of the pipe. Dia akan effect dekat dia punya losses. And then if let's say ada elbow, ada T, ada bentuk-bentuk berbeza, lepas tu dia ada valve, yang ni semua contribute to minor losses. So make sure you guys dapat bezakan mana minor, mana major. And kalau kita tengok dekat sini, saya buat colour lain sikit, dia ada pump. Pump ni dia bukan losses kan. Pump ni sebenarnya dia add energy, that's why dekat sini dia tak ada mention pula. Kat sini adalah dia bukan losses, dia add energy to the system, pump ni. Alright. So yang ni tak ada apa, yang ni lebih kepada perbezaan antara rough wall and smooth wall. Apa perbezaan dia dari bentuk, if let's say kita go through much deeper lah. And this is the surface roughness. So surface roughness tinggi, bentuk dia lebih ni lah. And kalau dia smooth, surface roughness dia berkurang. So major losses is caused by the friction at the walls due to the resistance of fluid particles as they roll, rub and slide each other. Bentuk dia macam tu. Okay. Guys, kita continue dengan head losses in pipes. So this slide and lepas ni kita akan go details on the differences in analytical calculations for major losses dengan minor losses. As explained previously, what is major losses? Major losses is caused by doing work against friction and due to friction kan. So macam biasa, the equations for calculating the losses is sama untuk major losses. Okay. So kita ada F L V squared over D 2G. Okay. So for lamina kita boleh guna rumus, and then for turbulent pun ada, tapi usually lah you guys just only need to remember or to memorize the friction factor for laminar flow. However, for turbulent, if let's say the question asks you guys to use equations, I am confident that the equation will be given to you lah. And if not, usually the question will ask you to use the Moody diagram instead. Okay, so I think for major losses should be no problems because we have done a few examples previously as well, right? So the second part is minor losses. So minor losses are caused by geometry of the pipes, sama ada bentuk dia vertical or horizontal, and also a presence of a valve, a fitting, and so on. Okay, so what is the differences is that untuk minor losses, the equation untuk kira the losses is a bit different as compared to major losses. For major losses, kita dah tahu kan, kita dah kira macam biasa, and dia ada this friction factor. However, for minor losses, we will use this equation. Okay, in which KL, this one, the KL is a loss coefficient. Loss coefficient ni yang kita akan cari, and depends on situations lah. KL maybe berbeza-beza. And KL ni pun actually kita boleh simplify by replacing this head loss ni, HL equals to delta PL over rho G ni, inside this equation. Yes, inside these equations, and then kita akan dapat this KL equals to 2 delta P over rho V squared. And the value of KL depending on the shapes that is involved. So in general, you guys need to understand that losses due to major losses, this is the important equations, and then losses due to minor losses, you will need to use this equation. That is the most important thing lah. Okay, so we proceed with minor losses. There are few things that you guys need to know about minor losses. Firstly is due to the entrance loss. Kan, macam saya mention tadi kan, dekat entrance ni, apa-apa entrance pun dia ada loss. This is loss to the minor losses. Okay, minor losses at the entrance, and this is the head loss when liquid enters a pipe from a large tank or reservoir. So kalau kita tengok kat sini kan, gambar ni, this is the large tank kan, dia dari luar, dia masuk ke dalam pipe, and then the value of KL, coefficient of coefficient, the loss coefficient depends on the shape of the entrance. If let's say it have a re-entrant, the value is a bit higher, and then if let's say the radius in which the flow will move into the pipes is ada lagi banyak radius, the value of coefficient of loss coefficient reduce kan. Kalau kita refer kepada gambar ni lebih mudah. Okay, so the value of KL will be reduced as the radius R over diameter lah, okay, meningkat. Okay, so means that radius lagi besar, lagi bagus lah. Radius lagi besar, lagi bagus. That is why kalau kita tengok dekat sini kan, sini 0.8, sini sharp edge, di 0.5. Sini ada slightly rounded, sikit je rounded pun dia dah turun. And then this one well rounded, lagi turun value dia. So this is the graph that you can refer. Okay, usually in the questions, sama ada dia bagi graph ni ataupun the value of KL will be mentioned inside the question itself. Okay, so this is the entrance loss. And then kita ada juga exit loss. Okay, yang ni lepas dia keluar lah. Okay, so usually for the head loss produced when liquid leave pipe and enters a large tank or reservoir. So dia terbalik dari sini lah. Sini daripada large tank or reservoir masuk ke pipes. So dia ada lagi satu loss waktu exit, waktu dia leave the pipe and then dia masuk kepada tank or large tank or reservoir. So at this condition, the entire kinetic energy of the exiting fluid is dissipated through viscous and effects and eventually becomes zero. V2 is equal to zero kan. Yang ni macam kita consider macam sebelum ni lah. Macam Bernoulli. Yang mana kalau last time kita consider V2 equal to zero. And V1 ada value lah. Kan? So for this condition, the coefficient of loss equals to 1. Exit loss from 1 to 2 is equivalent to 1 velocity head. KL equals to 1. Ini should take note you guys. Okay. Apa-apa loss due to pipes leaving and enters a large tank, kita guna KL equals to 1 terus. Okay. And thirdly, if let's say tengah-tengah pipe tu, dia ada sudden expansion or contraction, dia akan ada loss juga. Okay. So this is the graph for the sudden contraction yang mana daripada besar ke kecil, and also KL for sudden expansion. Dia expand daripada kecil ke besar. So this is the equation that can be used in order to calculate the value of loss coefficient. It depends on the diameter of at location 1 and location 2. So this is an important equation that you need to take note if let's say you would like to calculate the head loss due to the sudden expansion or contraction. And so kalau kita tengok kat sini, KL equals to 0.5 for extreme sharp edge entrance, and A2 over A1 equals to 1 if let's say no area change. So maksud dia A2 over A1 apa-apalah, tak kisahlah dia entrance ke contraction, A2 over A1 maksud dia if let's say A2 over A1 equals to 0, maksud dia tak ada apa-apa perbezaan pun lah kan. Area 2 dengan area 1 tu tak ada apa-apa no I'm sorry, A2 over A1 is actually apa yang menyebabkan A2 over A1 equals to 0? Mesti something like 0 over 1. So means that A1 ni sangat besar dan A2 sangat kecil, kan? A1 ni sangat besar, A2 sangat kecil, yang menyebabkan A2 over A1 equals to 0. Betul tak? 0 per something. And ini sangat besar, ini sangat kecil. This will menyebabkan A2 over A1 equals to 0, yang mana the loss coefficient will be equal to 0.5, or it will have an extreme sharp edge entrance. Dia consider sharp edge entrance lah dekat situ. Alright, so ini adalah KL equals to 0.5 kalau dekat sini lah. Okay, so if let's say A2 over A1, saya padam sikit, equals to A2 over A1 equals to 1. So means that A2 dengan A1 ni sama je in terms of their diameter. That's why area dia sama. So no area change means that KL equals to 0. no value for KL, and dia tak ada contraction ataupun dia tak ada expansion. Okay, so kita dah tahu so far tiga losses due to minor losses kan. So firstly is due to the entrance loss, secondly due to the exit loss, thirdly due to sudden expansion or contraction, and lastly due to head loss due to valve. Valve pun akan menyebabkan head loss juga. So actually untuk valve, the equation used to calculate the head loss masih lagi sama. Due to this is the equation to calculate the loss. Okay, sama juga macam yang minor loss yang lain, minor losses yang lain, and in which kita kena kira the coefficient of loss kat sini. Okay, kita guna yang ni. Okay, in which actually sama je dengan yang ni. Okay, cumanya kita guna pakai standardized, guna pakai losses, penyeraan losses yang sama dengan minor losses yang lain-lain, supaya kita pun tak confuse kan. Kita pakai yang ni, this one. Alright, so untuk friction loss due to valve bergantung kepada types ataupun conditions of the valve itself. If let's say the wide open, the value of loss coefficient is 0.5. If let's say the valve is 3/4 open, it is 0.5. If let's say a half open, it is 4.4, and lagi kecil, lagi tinggi dia punya loss coefficient. Okay, so dia bergantung juga kepada types of valve macam saya mention dekat sini. So yang ni adalah for all four gate valve, which is this one. So the value might be different if let's say the system is using different type of valve condition. Alright. Okay, so pump pula on the other hand, it is not actually a losses, it adds the energy. Okay, this is example of pumps, which is the centrifugal pump. So details I think you can read it by yourself on how the centrifugal pump is operate. So kat sini ada explanation dia sikit lah. So in details, in chapter 7 we will go through pump. Alright. And then okay, this is also some details on types of pumps and so on kan. So kalau kita ada pump, actually kita include the energy kan. Kita ada plus HP dekat sini. Okay, head loss pula due to minor losses dengan major losses yang kita kira sebelum ni lah. Okay, nothing much details here. Okay, so next power required by the pump, and this is some related equation in order to calculate for the power for the pump. So power is actually the rate of work or the rate of which energy is being transferred, and then how to calculate the power of the pump, rho GHQ, and then how to calculate the efficiency is here. So you will use both of this information in order to get the power and also the efficiency of the pump. So ini pun tak ada benda-benda penting sangat. Later if let's say those questions related to this part, you might refer to this slide lah. Right, so actually we almost done. So this is a general step in solving major losses yang korang boleh refer lah. So tadi kan saya dah mention pasal minor losses. Minor losses is depends on 4 situations kan. Satu adalah due to entrance, lepas tu dia exit, lepas tu dia sudden expansion, or contraction. And thirdly, kalau dia ada uh, valve. Ni minor losses. Okay, actually you need to consider also the pump lah. Walaupun pump ni sebenarnya bukan minor losses, dia actually add energy, but you need to take note as well. So for minor losses, this is the important factor that need to be considered, and also the how to calculate the head loss as well is given by different formula. Yang dia ada KL kan, KL V squared over apa saya pun nak kena tengok balik sekejap. KL V squared over 2G. Okay, over 2G. Okay, for major losses, saya just nak recap balik. First of all, kita kena consider, kita kena re-evaluate what is the characteristic of the flow, and also to evaluate, kita kena tengok the Reynolds number. Okay, if let's say the Reynolds number less than 2000 or 2300, we consider it as a laminar flow. But if it is more than 4000, kita consider sebagai turbulent flow. Okay, so kalau contoh, kalau laminar, macam mana kita nak dapatkan friction factor? Kita guna F equals to 64 over RE. Easier kan, sebab dia memang constant. And how to get the value of friction factor pun, kita just dapatkan the value of Reynolds number, and then kita boleh calculate the value of HL, in which kita guna HL punya equation tu lah. Okay, dan kita substitute the value of F. Okay, so untuk cases whereby the Reynolds number is higher, kita consider the flow is a turbulent flow, in which after that kita kena consider the surface roughness. Okay, for a given diameter pipes. Okay, daripada situ kita boleh dua cara, sama ada kita guna Moody diagram ataupun kita guna equation, tapi usually kita akan guna diagrams lah, and the equation selalunya pun kita akan guna diagram, in which can be considered as more accurate as compared to using the equations. And then daripada situ kita akan dapat the value of friction factor, and then friction factor kita ganti dalam rumus HL yang sama untuk dapatkan losses. So losses untuk kedua-dua major losses untuk laminar and turbulent flow, kita guna equation yang sama. Okay. Hey guys, and now we continue with a few examples related to chapter 6. Some problems that we are going to apply all the knowledge that we have learned in chapter 6. Saya akan tunjuk dekat sini lah. So this is one of the example. So the question asks to find the total head loss due to friction, valve and bends. So based on this information, kita dah dapat figure out kan, if let's say loss due to friction, kita dah tahu loss tu adalah major losses lah. So kita akan guna appropriate equations to find the losses due to friction. And then the other one is due to valve and bends, in which this can be considered as a minor losses. Okay, and also given that the flow rate is equivalent to 1.2 feet cube per second. So yang ni dia tak guna SI lah. So tak apa, kita just play around dengan dia punya quantity dulu. So this is the condition here. So diberi this is at position 1 and position 2. And then this is the valve. The valve is here. And then kita ada bend sini dengan sini. So what is other information given is dia punya tinggi lah. Perbezaan antara Z1 dengan Z2 adalah 12 tambah 13 equivalent to around 25 feet lah. Okay, so the question asks to find the total head loss. This total lah basically. So kita tahulah dekat sini, if let's say in this case H total equals to H due to major losses, okay, plus H due to the minor losses. Okay, alright. So how are we going to solve this question? So firstly, macam biasalah, kita kena dapatkan the general energy equation, in which also known as the Bernoulli lah. Okay, Bernoulli equation between point 1 and point 2 means here and here. So based on Bernoulli, kita kita add on the losses. Yang ni yang kita nak cari kan. Berapa losses dia sebenarnya. So based on Bernoulli, kita boleh cancel out mana-mana yang kita boleh cancel out. Contohnya pressure 1 dengan pressure 2 kita cancel out sebab atmospheric kan. Lepas tu V1 dekat sini kita boleh consider zero sebab dia dalam tank. Bila dalam tank, velocity of the liquid almost zero so kita boleh cancel out, and then what's left kita rearrange, kita akan dapat this equation, and Z1 equals to V2 squared over 2G plus Z2 plus HL, and then kita boleh dapatkan the value of HL terus, and HL ni is total loss lah, total head loss. So kalau macam sebelum ni saya cakap apa, HT kan, so tak kisahlah dia HT ke HL ke, sebab dia adalah combination of these major losses plus the minor losses. Okay, so kalau based on jawapan ni, maksud dia kat sini adalah HL lah kiranya. Kalau macam tu saya tulis sini lah, major plus minor losses. Okay, alright. So kalau kita tengok dekat sini, as information given here, Z1 minus Z2 adalah 12 tambah 13. So kita dah tahu this part will be 25 feet kan. So what else? Kita kena dapatkan this value of V2 kan. Macam mana nak dapat V2 kan? So based on last time kita belajar continuity, Q equals to A times V, and the flow rate equals to area of the pipe times the velocity, and then this V2 is equivalent to Q over A, given that berapa tadi, Q is 1.2 feet cube per second kan. Kita substitute and then kita divide by the area. Okay, so dia substitute here, dia divide by area. Area since kat soalan dia kata apa tadi, 3 inch diameter kan, 3 inch diameter, that is why based on 3 inch diameter pipe, dia akan dapatkan area 0.0491 feet square. So area macam kita tahu adalah pi r square lah. Okay, so dia ganti, dia akan dapat ni. Lepas tu V2 dia dapat 24.4 feet per second, and then dia replace dalam equation. Sekejap saya ambil colour lain sikit, and dia replace dalam equation ni 24.4 squared over 2G. Okay, G ni sekarang sebab kita tak guna SI, that's why 32.2. So for time being, just accept as it is as long as you guys faham the concept, then it is okay. Tapi for your questions later on, don't worry lah. So kita tak akan guna all these this can be called American units. Okay, so kita punya questions semua kita akan guna SI unit, so tak ada masalah. So total head loss kat sini adalah lebih kurang 15.75 feet. Okay, right. And now we move on with another example in which dia suruh kita buat apa ni, consider the figure below, determine the value of H, means Z, ZA minus ZB ni. Macam mana nak dapatkan this value? Okay, so given this figure. So apa kita nak buat? Firstly, macam biasa, kita start from the energy equation or the Bernoulli equations, and then kita simplify as much as we can. So based on these two condition, dua-dua atmospheric kan, PA dengan PB. So P1 kita cancel out, P2 kita cancel out, and then since dua-dua adalah dalam tank ataupun reservoir, big reservoir, kita boleh consider VA equals to 0, VB pun equals to 0. So V1 equals to 0, V2 equals to 0. So what else? Kita ada kat sini, kita tambah losses dia. Cuma losses kat sini kita bahagi dua lah, kan? Due to major losses, HF, which is the friction, and also the minor losses. Kita tambah dua-dua. Kan? So ini dah settle. Lepas tu kita rearrange, kita akan dapat Z1 minus Z2 equals to HF minus HL. Okay. And then no, this one is not minus. This one is Z1 minus Z2 is HF plus HL. Okay. So Z1 minus Z2, Z1 minus Z2 is actually the value of H lah, kan? Ketinggian ni ZA minus ZB lah yang kat sini. A ni kira 1 lah, B ni kira 2. So Z1 minus Z2 is H. Ini yang kita nak cari sebenarnya, kan? So kita dah tahu H equals to HF plus HL. Okay. So kita kena cari what is HF and what is HL. Kita tahu dah tadi major losses HF, minor losses HL. So untuk major losses, kat mana major losses dia? Kita boleh dapat friction dekat sini dengan friction dekat sini. Ada dua tempat. That is why kita ada dua terms kat sini. Kalau major losses, kita guna this equation. Ingat lagi kan? Dia ada friction. Friction factor dekat sini. Lepas tu length is length of the pipe itself, and then V is the velocity lah. Okay. And then D1 is for diameter 1 and D2 is for diameter 2. Kalau kita tengok dekat sini, D dekat sini lain, D dekat sini lain. Ini sekadar teori lah sebab dia tak bagi any information. So kita just tulis macam ni. That's why dia ada dua term. Satu term, dua term disebabkan dia ada satu pipe dekat sini, satu pipe dekat sini. Okay. Alright. So that is on the major losses. On the minor losses, kalau kita tengok sini, apa minor losses yang kita ada? Okay, sekejap saya padam sekejap. Minor losses. So firstly, kita boleh tengok dekat sini, dia ada entrance losses, dia ada exit losses, and then dia ada sudden expansion losses. So kita boleh kata dia ada tiga part. Satu, sekejap saya padam yang tadi. Ini untuk minor. Sorry, saya buat ni balik. Okay. Satu adalah losses due to the entrance. Nombor dua is due to the sudden expansion, kan, daripada pipe kecil kepada pipe besar. Dan ketiga adalah waktu dia exit losses. Okay. That's why kita ada KL1 in which this is the entrance losses. So this one is K122, this is the sudden expansion losses. Okay, and then kita ada this exit losses. So what is the value of H? H is apa yang dia nak cari, kan, dia nak suruh kita cari. So H is equal to HF plus HL, in which this is HF, this is HL. So semua ni adalah value of H. And if let's say the questions give all the information, then kita replace je lah all the value here, and then we will get final value here. Okay. Right. Okay. Now we proceed with yet another example. Okay. So kita baca dulu soalan dia. A tank of water empties by gravity through a horizontal pipe in another tank. So dia ada tank 1 and tank 2. There is a sudden enlargement, dan dekat sini sudden enlargement in the pipe. At a certain time, the difference in level is 3 meter. Okay, given that Z1 minus Z2 is equals to 3. Okay, and each pipe is 2 meter long. Okay, so kita tahu untuk pipe ni, yang pipe ni dua-dua sama panjang lah. Ini dengan ini. Ini 2 meter, ini 2 meter. Alright, dia punya L L. Okay, and has a friction coefficient of F. Dia pun sama. Sama dengan 0.005. So senang lah kita nak kira major losses dia. Okay, so the inlet loss coefficient is 0.3. Oh, dia bagi tahu dekat inlet sini. Inlet sini akan ada loss. Kat sini pun akan ada loss. Kat sini pun akan ada loss. Kan? Inlet losses dia dah bagi KL1 0.3. Okay. KL1 0.3 dekat sini. Okay. Sini dia tak bagi. Sini tak ada. Okay. Alright. So, macam mana kita nak start? Dia siap. Sebelum tu dia tanya apa? Ni yang paling penting. Dia nak suruh kira flow rate. What is flow rate? So macam mana kita nak start? As usual, kita start dengan Bernoulli equations, and then kita cancel out yang mana kita boleh cancel out, since P1 and P2 is exposed to atmospheric pressure. Kita cancel out P1 and P2. Lepas tu dua-dua dalam large tank reservoir. P1 and P2 pun kita cancel out. And then what else? Itu okay. Alright, and then HT equals to Z1 minus Z2, in which given Z1 minus Z2 equals to 3, and then kita tahu total head loss adalah 3 meter. Okay, tapi this is not the answer that the question asks us to find. So the question asks to find Q. Okay, so based on this information, kita kena cari Q. Nak tak nak, kita kena buat satu-satu juga. Okay, so for major losses, kita ada dua major losses due to pipe yang ni dengan pipe yang ni. Okay, so kita tahu this is the equations. The F is sama untuk kedua-dua. Okay, the difference is that in terms of dia punya dia punya diameter. Diameter, the first one is 20 mm, the second one is 60 mm. So sebelum tu, ini adalah supposedly L time V kan. Tapi daripada continuity kita boleh tahu V equals to Q over A. Okay, sebab kita nak cari Q. So everything must be Q in the equations. A ni kita gantilah. A ni pi R square kan. So kita guna and then 2G D. Okay, ini pun length pun standard 2 kan, sebab dia kata apa tadi, dia punya length adalah 2 meter and 2 meter sama. Alright, so kita selesaikan, kita dapat major losses at pipe 1 dengan major losses at pipe 2 in terms of Q, flow rate. But we are not done yet. Kita baru dapatkan major losses, and then kita kena dapat the minor losses pula. Minor losses macam saya cakap tadi, ada 3 tempat. 1, 2, 3. Waktu dekat dia punya entrance, waktu dekat dia punya sudden expansion, dengan satu lagi dekat dia punya exit. Kan? Alright. So untuk yang pertama adalah dekat dia punya entrance. Entrance KL1 adalah given 0.3, betul tak? Dia kata apa tadi? Loss coefficients, the inlet loss coefficient, which is the entrance is 0.3. So kita ganti 0.3, yang lain pun sebab dia punya diameter is 20, and then kita replace, kita dapat entrance punya. Okay, so untuk sudden enlargement kita boleh find dia punya KL sendiri. Kita guna rumus ni sebab kita tahu dua-dua diameter ni. Kita dapat KL2 is 0.79. Kita replace masuk dalam equation to find the loss for sudden enlargement. Kita akan dapat this value. And then lastly, untuk dekat dia punya exit, KL dia adalah 1. Ingat lagi tak? Kan, sebab dia bila dia masuk ke satu tank yang besar, kita consider KL equals to 1 dekat dia punya exit. Kan, ada mention kan sebelum ni. Kalau ingat lagi, sekejap saya cari balik. Dekat atas, dia macam dekat bahagian atas sikit. Sekejap. Okay. Dah ke belakang sangat ni. Okay, this one. Exit loss from 1 to 2 is equivalent to 1 velocity head. Okay, since the head loss produced when liquid leave pipe and enters a large tank reservoir. So ini condition sama dengan yang kita buat soalan tadi lah. Okay, sekejap kita bagi balik ke soalan, which is this one. KL equals to 1, atau kita dapat ni. So kita dah dapat dua terms untuk major losses dekat pipe 1 and pipe 2, dan untuk minor losses kita dah dapat satu untuk kita punya entrance, and then satu untuk kita punya sudden enlargement dekat sini, dan satu untuk kita punya exit. Kan? Lepas tu kita buat apa? Kita replace sahaja semua. Dua depan ni untuk major losses, yang tiga ni belakang ni untuk minor losses. And then we replace HT ni, kita dah tahu dah sama dengan 3 tadi. Okay, and then kita replace, kita dapat the value of flow rate. Okay, senang je kan? As long as you guys understand the concept, then it should not be a problems. Okay, before we end chapter 6 ni, kita go through yet another example. As shown here, figure below shows the system using pump. Also, yang ni dia introduce pump. Pump ada dekat sini. Okay, to pumping the fluid from A to B. Okay, pump ni diguna untuk pump the fluid from position A to position B. So the question asks to find the energy added by a pump. Berapa energy yang added by a pump here? Okay, so this is all the information given, which can be seen in the picture here or in the figure here. PA equals to minus 28 kilopascal, PB equals to 296 kilopascal, and then there are 2-inch steel pipe here, and then sini 3-inch steel pipe, and the elevation difference between ZA and ZB adalah 1 meter. Okay, alright. So also given is the flow rate and also specific weight lah, 8.44 kilonewton per meter cube. And also given the head loss due to friction and also fitting and stuff is 1.86. So kita tak boleh cari dah. The total head loss adalah 1.86. Bila dia kata ada due to friction, fitting, maksudnya dia dah tambah lah minor losses plus the major losses. 1.86 Newton meter per Newton meter. Okay, apa Newton meter per Newton ni? Okay, this is supposedly to be meter lah, head loss. Sorry. Okay, so as usual, apa yang kita nak kena buat yang untuk memudahkan kita adalah kita guna the Bernoulli equation or the general equation at position A dengan position B. Cumanya untuk this case, since kita add on pump, so kita tahu kan, macam saya terangkan sebelum ni, bila kita tambah pump, kita tambah energy. That's why in the energy equation, kita tambah plus HA dekat bahagian kiri. Tapi dia ada losses juga. Dia tambah HL dekat bahagian kanan. Okay, so HL ni is given actually, kan? HL is given equals to 1.86. Right, so HA, kita rearrange balik semua ni, kita akan dapat HA equals to HL plus PB minus PA over rho G plus ZB minus ZA plus VB squared minus VA squared over 2G. So, in order to find the power, and the question ask kan, the energy added by a pump, berapa energy added by a pump is this value lah, HA yang kita nak cari. HL given, no problem. PB minus PA over rho G given juga sebenarnya. PA negative 28 kilopascal, PB 296 kilopascal. Dan kita replace, kita akan dapat value for second term here, the purple highlighted area kan, sebab kita boleh replace je this value kan. Rho G ni 8.44 lah, specific weight kan. Alright, specific weight in which is given Okay, and then the blue shaded area ZB minus ZA also given, and this 1 meter. Alright, and then the final or the last terms VB squared minus VA squared, this one kita kena work out sikit lah kan. Macam biasa kita tahu flow rate equals to VA, so the velocity is Q over A. Since the Q, the flow rate is given, so kita boleh find V1 and V2. Okay, so V1 and V2, the differences is actually dekat dia punya area je lah. Since dekat VA adalah 3 inch, VB adalah 2 inch. So bila kita replace dalam A, kita akan dapat VA equals to 2.94 meter per second, and then VB 6.46 meter per second. And then kita replace dalam ni, kita akan dapat 1.69 kan. So sekarang kita dah tahu HL equals to 1.86, the second terms equals to 38.4, the third term equals to 1.0, and the last term is equals to 1.69. So kita dah tahu the added energy by the pump is when kita added all these terms, and then kita akan dapat 42.9 meter. Okay, alright, I think that is all for chapter 6.